Hello, everybody, and welcome to, DevRel Talks, Google Cloud Talks by DevRel. My name is Yufeng Guo. I'm in Cloud DevRel, and thanks for joining everyone today. Let me change this layout. If you're joining kind of either later on during the day or you leave and you come back, and if this live stream, maybe it's not going or something, there's a YouTube live link that you can also join. And so we're broadcasting there as well. So hi to folks watching on YouTube live. And so, today we're going to be covering Google Cloud Platform's AI platform kind of product line. We're going to cover topics both in terms of how to get started and what is on tap, as well as topics around explainability, forecasting with my colleagues Sarah Robinson and Carl Weinmeister. So we're really excited to have you here today. And with that, it is 9:15 in Pacific time, 12:15 Eastern, and some amount of hours later. Ooh, someone says they can't hear. Can anybody else hear me? Audio is okay. Okay, that's good. Hopefully, if you can't hear me, turn on your audio, make sounds, things like that. And with that, let's get things going here. I'm gonna tweak the audio on my side. Let's see. Everyone seems to be able to hear me. And let me go ahead and start presenting then. It appears that for whatever reason, I don't have the option to present. This is what I get for joining from a different presenter account, I suppose. So let me tweak that. Just give me 1 second here. We're gonna re-unjoin from an account that I can present from, and with that done, let's see here. I'm back. Oh, the video is very blurry. That's also good feedback. And let's go and let's see. Yeah, we have some comments from YouTube Live. They said the video on YouTube looks a little bit better, but let me switch over. Okay, so I've swapped over. Hopefully you can still hear me. Bear with us one moment here. Now I'm going to start presenting. Let's present my window and choose the window. And all right, I think we are ready to go. And I'm going to move over to the view on here. And I think we're set. Say something if you can't see the presentation, but hopefully folks are okay here. And so today I'll be covering kind of an intro kind of topic. We'll cover everything from the data labeling service and notebooks to running serverless training and production kind of deployed models, all the way to pipelines and how to get hands-on to things like TensorFlow Enterprise and how to access that. So it's a bit of a whirlwind tour of Cloud AI platform, and we'll be trying to cover that in the next 30 to 40 minutes or so. And if you have questions, you can drop them in the slides. I have a Q&A tool here that I can trigger. Right, so you can ask questions at that link, and I'll be able to see them. Let's see, let me turn on allowing questions from everybody, and we have our Q&A up and running. Great. And folks on the live stream on YouTube can also feel free to drop questions there. Always happy to get those as well. So with that, let's get started. The link of the Q&A is at the top of the slides. It's literally on every slide. So hopefully you won't miss it. It's right at the top. All right. So the first thing I want to cover is kind of what does AI platform try to cover in terms of use cases, and what abilities does it unlock? Right, where over the last few years, of course, machine learning and AI has become this big topic. And one of the things that has now become very much recognized is that it's a team sport, that it takes a village to create a machine learning powered infrastructure application company. And so having this kind of team and sports team almost mentality, the idea was to build a platform that can support that kind of workload. Everybody from the data engineer and data scientist all the way to your team of analysts, and having the right tools for all of them along the way, and being able to transition from one to the other as kind of time goes on. So this brings us to this brings along with it several technical challenges, right? Building a platform that's suitable for a wide audience is admittedly not the easiest task. Anytime you're trying to cater to a wide audience, everybody kind of has different needs, and so you end up with a platform with a number of different tools that are serving a number of different users. And so some of the questions that come up when you think about how to make a faster or better impact on your business or on your kind of environment or workflow, things like how do you prepare data better, faster, easier? How can you get your models that you're experimenting with to a production state and deployed more easily, and manage its lifecycle so that when you want to deploy a new model, you can basically easily transition, roll back, split test, things like that. A lot of ideas from kind of traditional software engineering in a lot of ways. And of course, being able to do this in a flexible way, build and deploy both on local environments as well as in cloud, maybe some hybrid of the two. And of course, in this day and age, especially now that we are all kind of spread out and virtual, collaboration is more important than ever. So with that in mind, some of the pieces that AI platform has now incorporated, to address these, I've kind of listed out in this slide. I won't read all this text, but my hope is that over the next the remainder of the presentation to kind of show us how exactly we achieve all of these different points through the use of AI platform directly. So we'll kind of switch between the slides and the actual tool itself, because I really like to get into the weeds and show you exactly what it looks like to use it, not just talk about it, right? So with that said, the first thing to talk about is the data labeling service. And I'm going to switch over to the tab here. If I'm in my project, in Cloud Platform, if you have an account, you can follow along if you'd like. Hit that hamburger navigation menu up in that upper left corner, and that will open up this long list of products. And GCP has a lot of different offerings, and AI Platform is kind of at the very bottom of the list. The reason for that is above my pay grade. But at the very bottom, there are partner solutions. And if you scroll up from that, there's other Google solutions. And if you scroll up from that a little bit more, you get a list of kind of artificial intelligence or AI solutions. And so under AI platform, we can click on that. I know there's a flyout, but we can click on that, and that'll bring us to this view, this dashboard view. And there's this kind of sub menu that we can then kind of go through, and we'll peruse a number of these today. You might also have a view that looks something like this, where the icons are like that, and it kind of comes in and out. You can toggle that with this button on the bottom left, this little arrow, so that will lock its position so that you can always have the words showing, or if you want to save some screen real estate, you can lock it back and just have the icons and have it kind of dynamically going back and forth. So with that, onwards to the data labeling service. That is located, let me go back and actually show you exactly where it was located. I'm going to leave this open so that it's easier for folks to follow along. The data labeling service is the third item on this list here. And you can basically use the data labeling service to create labeling tasks. This is a way to get your data, unlabeled data, to be labeled by human labelers. And so that's the overall objective of the data labeling service. And you want to, let's say in this image, identify different segments of the image of like, where's the laptop, where are the people in this image, and didn't mean to go forward. And the idea is that there's kind of three different, you can call them concepts in this tool. And so as a brief overview, you can create data sets, but really you want to create data sets that are unlabeled, right? And you make that. And then once you have a data set that is unlabeled, you also need to go ahead and make what's called a label set, which is kind of an interesting name, where you basically just define the possible labels. So in this example, I have a data set of flowers, and I've created labels like tulips, rose, daisy, neither and both. And that's also important if you want to be able to help your labelers be able to accurately label your images. Say you have an image, you thought there was a flower in there, but maybe there isn't. Or maybe it's not one of the 3 types of flowers that you have. And then finally, you need instructions. They are human labelers, so you've got to write up some instructions for them to follow. And the tool right now accepts instructions in the form of a PDF. And so I've uploaded a PDF to cloud storage and kind of pointed there so that the labelers can see that. All right, so let's see. There's a quick question someone asks. What is the max set of labels that can be used? I don't know. Can folks see? Yeah, this presentation where I tried to present the question, but oh, it's on the slides. There we go. What's the max set of labels that can be used? This is kind of an interesting thing. Google Slides has Q&A. It's fun. Asked by Trish Wetzel. I know there's a limit. I don't remember offhand what it is. I want to say it's 1,000. But if we had more time, maybe on like a live stream that we dive straight into data labeling service, we can definitely find that out, Trish. But I think offhand that it was 1,000 labels, and that's just a technical limitation that I'm sure they'll raise down the road as well. So it's kind of an initial thing. I want to say data labeling service might still be in beta, though it doesn't say it here, so maybe it is into GA now. So with data labeling in place, the next kind of piece of the puzzle then is what every data scientist or data engineer wants to get their hands on, right, is a notebook. How can you get me a notebook with the right environment configured, and I could just get started on my work? Because installing libraries, managing versioning of dependencies is, nobody enjoys doing that. They want to get to working on their data, working on their code, training their model. And so Google has this product called the Deep Learning Virtual Machine Image, Deep Learning VM Image, which basically has all of that solved for you, even including installing GPU drivers in terms of installing CUDA for us, and so that we don't need to worry about that either. And so we can basically just pick the machine we want, pick the image that we want, and we're off to the races. And so the idea is that there's not just the image and the drivers, but also common libraries that we might want to use. TensorFlow, Keras, PyTorch, XGBoost, all of your SciPys and sklearn and matplotlibs, all of them already living there. And best of all, there's a proxy for accessing Jupyter. Because typically, if you were to, say, configure your own deep learning image, right, a custom machine image, load it onto a compute engine and start up Jupyter Lab, how would you actually access it? You would end up needing to, let's say, basically do a normal just port forwarding, right? You do G-Cloud Compute, SSH, and there would be a -L, and then you would port forward 8080 to your local 8080, and then you can type in localhost :8080, and you get to Jupyter Lab as if it was running on your local machine. But that means you have to install G-Cloud, authenticate it to your cloud account, and then you can run these commands, and then you have to kind of leave that SSH window open. So if you don't want to do all of that, now GCP has this kind of AI Platforms notebook feature. So if I go to AI Platform again, if we go back to where we were, and we go down to notebooks. So AI Notebooks basically wraps deep learning virtual machines with a reverse proxy. And so now we get this nice button. I can literally just click this button. I don't need to run any SSH, and it just opens it in a new tab. You'll notice that in this new tab, the URL is not localhost 8080. It's an actual HTTPS web address. And so because of that, you can access it, and it's authenticated and all that good stuff. It's not just obfuscated. So if somebody on the live stream or on Hangouts wanted to copy that link down and type it into their browser, that's not going to take them to my virtual machine, of course. And because it's Jupyter Lab, I can also have things like a terminal, and I can run commands directly here as well. So it's like having an SSH window, but also Jupyter on top of it, which is awesome. Let's see, we have a couple more pieces here. So after we have notebooks in place, then it becomes a question of, okay, notebooks are nice, but I can only go so far with notebooks, right? It's a place to do experiments. It's a place to do kind of data wrangling, a little bit of exploration. But at some point, once you have everything set up, it would be really nice to have something that's more repeatable. And for really large data sets that you might not want to run on a local environment, something that's scalable. And so AI Platform also has, in addition to data labeling and notebooks, which somebody might look at that and be like, yeah, that's pretty much all I need. There's this notion of AI Platform's training. And so there are training jobs that you can create and kick off, both from the command line and API, as well as from the UI. And so there's a couple of different ways kind of to do this. There's just normal kind of AI Platform training, which supports a number of different libraries, TensorFlow and PyTorch and sklearn and things like that. But then on top of that, there's also what's called custom container training, where you can literally just supply a custom container with whatever libraries you want and train it up that way. And then there's also layered into that is the hypertuning service, and there's a hypertuning library that you can kind of hook into your code. So here's an example of that. Here I did some custom container hypertuning across 20 trials, and you can see I was tuning loss, learning rate, and momentum. And I can scroll to the right, thank goodness. And I have some metric, and you can see that each one took 7 minutes, and it ran across 20 trials. And once I kicked this job off, which took 20 trials, 7.5 minutes each, and it took a couple of hours, I didn't have to sit here and monitor it or watch the logs. I can just let it run. I could go and tweak my code and kick off another job. I just don't need to monitor it, which is really nice. And here's one where I was tuning ResNet, and there's 32 trials. Each trial was 13 minutes. That's basically your whole workday there if you were kicking off these trials and experimenting with it manually. So this was really quite nice. And I mentioned there was also a way to kick off training jobs from the UI. So there's this new button. It's in beta. Google Cloud Platform, AI Platform has built-in algorithms. So we can do custom or built-in algorithm training, which allows you to, if the UI will cooperate, select your choice of algorithms, both in terms of structured data and image data. And that allows us to kick off training jobs from the UI. And I have some more screenshots of that to explain kind of the flow later in the presentation. And then continuing our whirlwind tour is deploying, right? Once your model is trained, you want to be able to deploy it and have that scale out. For those of you familiar with things like App Engine, which can scale up and down automatically, your web service typically is what folks use for. A lot of times you see questions about people who have trained their model and then they want to scale it, right? They want to be able to deploy it somehow. And because we're in a Python world for the most part with deep learning and machine learning models that are being deployed, oftentimes the recommendation is, just wrap it in a Flask server, right? Or and in that Flask server, you can run whatever code you want. You could just import it and just have this model running locally in Python, and that might work depending on your use case. If you only need to make predictions once a second, once every couple of seconds, maybe it's just structured data, like you can get away with that. But when you start to scale up, when you start to running things in production, you're going to want a more reliable system. And so AI Platform prediction, which you can find in this models tab. So jobs are training and models are prediction, which apparently I can't click. There we go. You can create these models, which is really a wrapper around this concept of versions. So you can create lots of versions as you create new models, for instance, and you layer your new learnings on top of each other, and you can switch between them and choose one for default and switch between them. And the nice thing about this is that it will allow you to scale automatically. You don't need to kind of figure out how much demand am I going to have. I need to allocate resources to that. It'll just do it for you. And when the demand lowers, it'll come back down. And so that piece of it is super convenient, because if you watch this, the way the UI plays out is when I create a new version, I give it a name, I give it a description, but the really meaningful the meat of it here is choosing your Python version, choosing the framework that you used, including a custom prediction routine. So if you want any code to run before it calls your actual model, you can do that. And at the end of the day, the real crux of it, lies here in giving it a model URI, which is just the cloud storage path where you've uploaded that exported model, and your code just needs to be able to handle loading it in, right? And so you can see, say I choose TensorFlow, and I can choose a number of different framework versions going back to TensorFlow 1.0, but including the most recent releases around 2.1 and 1.15. So a lot of options there, and you can also, I believe, you can choose manual scaling if you want. I'd recommend auto scaling and just setting a minimum number. So if you want to make sure things stay warm, you can say like 2 nodes at a minimum and just let it scale up from there. So that kind of workflow, when you tie in data labeling, notebooks, training, and prediction with the broader Google Cloud ecosystem of data management tools like PubSub and BigQuery and Dataflow, as well as visualization tools like Data Studio, you begin to see how you can piece together an entire workflow that can serve lots of different users at different points along this pipeline. You don't have to learn how to use every single one of these tools yourself, but across an organization, everybody can touch some different piece of this, and they can all fit together into a useful and very powerful and scalable, importantly, workflow. And so now with a little more detail, I'm checking the time. I'm trying to think, when are we have till the end of the hour. So we have a good amount of time to dig into this more and check out the questions and things like that. So really excited to get more into this. So let's take a look more at the data labeling service first and foremost. So I mentioned you got to add a data set, and once you have that data set in place and you create the labels and you create your instructions, what we'll do is we'll create what's called a labeling task. And if I can zoom, apparently I can't. Must have disabled that on my mouse or something. A labeling task is a way to describe how to link together your data set, your label set, and your instructions into one labeling task. And then that'll get sent off, and you can kind of request multiple reviewers per item if you want. Not just one, but maybe 3 or 5. And the system is smart enough to basically send out these tasks to different people and make sure they agree. So in the example of having, let's say, image classification, you would have, the first labeler say it's a car, the second labeler maybe thinks it's a truck, and then the third person is the tiebreaker to figure out, okay, let's disambiguate between these two. And once you have your data labeled, you can then export that labeled data, right? And now you're ready to use it in a place like notebooks and your training jobs and so on. And so the goal here is then you would end up with high quality labeled data that you can use. And that then, of course, flows nicely into the notebooks, as I mentioned. And so this is a slide with lots of colorful circles. And yes, so the notion around the notebooks being one click, let me show you exactly what that looks like. So I've got a couple of notebooks here, but what you care about is how you make your own, right? So up here, there's a new instance button. And so by clicking that, you can choose a number of different options here that are pre-configured, everything from TensorFlow 1.15 as well as 2.1. And importantly, you can also choose lots of different models, but moreover, there's this customized instance. This button I really want to call your attention to. I know it's not the biggest button here, but if you click Customize Instance, we'll see that now we can choose everything from the region and zone that you want your VM to live in, as well as the environment that you want it to have. So this might look familiar because we kind of just saw some of these. There are your TensorFlow images, there's your PyTorch images, there's even R, Rapids, and a number of Intel optimized base images. You can add environment variables of your choice to the image itself, right? And so you can say something like, your SQL, connection string, you can give that a value. Or you can have some useful things there, and then you can then have that image shipped across your organization. You might want to choose a different machine, right? N1 standard 4 is just 4 CPUs with 15 gigs of RAM. I bet there are those of you out there today who are watching who have more powerful machines than just 4 CPUs and 15 gigs of RAM right now, just to watch a live stream. So if you're going to be doing some deep learning modeling, you might want something more. Maybe you want 8 CPUs, maybe you want 32 CPUs and 120 gigs of RAM. It really depends on your use case. And you'll notice that there's a number of other menus here for both high CPU, which is saying it's high CPU relative to the amount of memory. And then high memory is the other way. It's saying it's high memory, but it's specifically high relative to the number of CPUs. And so it's that ratio that we're playing with here. So there's a lot of different types of machines that you can choose from. And the N1 and N2 items are referring to, if I recall correctly, what types of chips are under the hood. So E2 is efficient instance. So that's, I want to say that because it's power efficient, it might be cheaper or something too. I haven't played around too much with that. And let's see. And then of course, everyone's favorite topic, GPUs. Having GPUs and potentially more than one GPU attached to your instance can enable all sorts of interesting things, up to 8 V100s, which comes with it the associated costs of running that. So make sure you turn off your instance when you're not using it, especially if you're going to be attaching a lot of resources. And be sure to hit this checkbox, this install GPU driver automatically. That will take care of installing the NVIDIA graphics drivers on there so that you can use CUDA, get that acceleration, get that benefit for that GPU you are attaching. So we'll leave that checked in so that the red text goes away. Finally, there's a number of options here that are kind of folded up. I want to call your attention to the boot disk because this will give us the option of choosing an SSD persistent disk or a standard kind of spinning hard drive persistent disk and choosing its size. And once this is created, the important thing, I'm going to hit cancel so I can go back to one that I already have. One thing that is worth pointing out is that for any given machine, when I click on this menu, so pay attention to what it says here. It's AI platform, and actually I'm going to make this smaller. Just look at the logo. There's this brain, and it's notebook instances here. When I click on this notebook instance and I go into kind of the details of it, watch what happens to the UI. It changes, right? It's not the brain anymore. What is this? It's a little chip. It's compute engine, right? Because it's compute engine under the hood that this virtual machine is running on. And so now we see that we have all the controls that you would get with a standard compute engine virtual machine. And so that means I can click edit and I can do things like take a snapshot, make a machine image, add labels, tweak the network interface, change firewalls, add tags, and add additional disks. So you could have perhaps existing persistent disks with data on them, and you can attach them in, say, read-only mode, and you could attach that same disk in read-only mode to multiple machines. So you could have a data set, maybe a huge data set, multiple terabytes worth of data, and be reading from that same spot across all of your VM instances, across your team, across your organization. And then, there's a bunch of custom metadata that's already added for you. And of course, you can add more for yourself that you want to use. So that's kind of my spiel about the under the hood of AI platform notebooks, because it's just a virtual machine and you get all the niceties, including Stackdriver logging and being able to, you can create similar directly from here and things like that. So it's really quite handy being able to work with that. And you see when I go back, it takes us right back to AI platform. So the redirect kind of works nicely there. Okay, I think I just talked through a bunch of slides, so I'm going to potentially skip forward a little bit. Oh yeah, this is actually worth pointing out, is that they did add some niceties to this UI in that these two images are stopped, right? The machines are turned off. And so I can actually use this drop down right here and very quickly, in literally one click, I'm just mousing over these numbers, right? A single click, I can change by clicking on this number or this number, I can change the configuration of this machine or just take the VM off or take the GPU off. And so now you see it's doing the configuration. I don't need to click this, then go to edit, then change the GPU, and then back all the way back out like we kind of had to do for, say, attaching a persistent disk or tweaking the network. So now you can see the GPUs are gone. Let's see, right. Having this live inside of your project means that you have all of the authentication built in. You can import data from GCS. You can go and get stuff from BigQuery and from Cloud SQL, wherever you may have your data inside of your project. And it even supports a BigQuery magic. So in Jupyter, there's this %% BigQuery command that you can then just write your SQL right underneath without having to kind of wrap it as a Python string with the triple quotes and things like that. As we mentioned, it runs on Compute Engine, so you get everything that Compute Engine gives us. And because it is authenticated to your project, it means you can use the CLI and API calls to AI platform training. So you can deploy jobs, you can push to models directly from your notebook, which can also be a decent workflow. And so that's all connected. That's kind of what we were talking about. And you can choose any instance type. We talked about that. We talked about adding GPUs. And the image that backs it is called this deep learning VM. And that actually doesn't live here in this UI. Let me point that out. For whatever reason, whenever I make the font really big, this search button dies. So you could click that and search for Marketplace. I'm going to go over here and click on Marketplace. And I can go and I can search for solutions. So I can go to this deep learning VM and we'll get this result. And so you can launch, this is through Deployment Manager, you can launch deep learning VMs directly from here. And you can make sure you choose to install GPU on the first startup and enable access to Jupyter Lab. So this gives us that nice SSH kind of reverse proxy built in. And this gives you access to tweaking network directly. And it's pretty much the same thing. The reason I point this out mostly is in case you want even more control, or if you want to deploy this to other environments or take this deployment and tweak it and things like that. The final thing I'll call out is that this all runs on this new-ish thing called TensorFlow Enterprise. These are special releases of TensorFlow that are optimized for Google Cloud. They are more performant and, more importantly, promise kind of this long-term support similar to like a Linux model, right? So it means that we will support certain versions of TensorFlow for the next 3 years and backport bug fixes and offer enterprise support for the users here. So you can kind of trust that it will work. And I think that's, yeah. And AI platform training uses it under the hood anyway. Of course, there's notebooks and things like that. So it kind of is just under the hood. This is what's kind of happening is TensorFlow Enterprise is what's being run. We're not literally just taking the open source version and just running it vanilla. We made it work extra well on Google Cloud. So you can trust that it'll work as ideally as it can on GCP. And so this is an example of how you might kick off a training job from your notebook. And you'll notice here, I don't have to specify anything about TensorFlow Enterprise. It just kind of works. And let's see, serving the model from the notebooks looks something like this. I mentioned how you can do it from the notebook. This is kind of an elaborate bash version where we're pushing the model directly. So this is a bash script. You see that at the top, the magic %% bash. You can also use the API or the command line interface, since you can use the exclamation point to shell out and create models that way via exporting a model to cloud storage. And so we talked a little bit about AI platform prediction, this kind of scalable hosting, and you can also do hosting now with GPUs attached to it for even faster predictions, especially when it comes to predictions on environments where you're doing predictions on images or maybe even video. And so you can do both online predictions, so live, one request, maybe there's a couple predictions in there, or huge batches of data where you don't really care too much about hearing back immediately, but you do want to hear back soonish, right? So you can send a batch of data. Here's a file, or here's a folder filled with all this data I want you to run predictions on. Give me your inference, and then I'll pick it up later. So that's kind of the overview of this tooling, right? Going from the data labeling to notebooks to manage training and serving, as well as how it all connects to the rest of AI platform. And so with that, I want to turn to the questions, the Q&A. So you can see the link at the top. We have about 10 minutes to do Q&A, and we can see what questions folks have. And maybe with time allowing, we can answer Trisha's question definitively on the max set of labels that can be used, and that would be really nice too. So let's push the first question here. We have an anonymous question. How does AI platform play with GCP Data Lab. Is AI platform more feature rich and will eventually replace Data Lab and is the next iteration? So Data Lab, for those who are not familiar, is kind of was a notebook solution that Google made several years ago, and it lives somewhere in the UI, if I can find it. If anyone knows where it lives, I would love to hear from you. Let's try this search button. All right, come on. All right, I'm gonna have to zoom out to make this search button work, apparently. Data Lab. I don't know if Data Lab is still available as in the UI. So, I mean, the short answer is, we recommend that you use AI platform notebooks as the de facto solution. Data Lab kind of provided a wrapper, UI wrapper around notebooks. So if you're ready to transfer over from Data Lab, if you don't have like huge dependencies on it, the recommendation is to use AI platform notebooks. You'll have vanilla Jupyter Lab. You have the entire Jupyter ecosystem. You can install all the plugins you like to your heart's content. And since it's running a virtual machine, you can pull in your Bash RC and things like that you like in Bash as well, and customize everything just the way you like it. So hopefully that addresses that question. The next question here is, what aspects need to be taken care of to understand the cost incurred in running these jobs? That's a great question from Dharmesh. And there's a couple of pieces to there, right? One is when you're making a new instance, and if you click customize instance, or actually let me show you one more little trick here, is you can, when you go to new instance, instead of just going straight to customize, you can have a few things pre-filled. Say I know I want TensorFlow 2, and I know I want GPUs, but maybe I don't want a T4. So I can click this and be like, okay, am I committed? I'm not quite committed yet. I can leave the name what it is. I'll get a chance to change it shortly. If I scroll to the bottom, while the create button looks very enticing and you want to click it, instead click customize. Right? And so that'll take us to that same menu, but it's going to pre-fill some of these things in. It's got the T4 already filled in. It's got the count in. Maybe I want a P100 instead or something like that, or a V100. Maybe I'll change the name. Maybe I'm on the East Coast of the US, so maybe I'll change it to US East instead of US West to reduce latency. Things like that. And you'll see on the right-hand side, as I'm tweaking this stuff, the number's changing. Well, of course, changing the software under the hood won't change the cost, but if I change the machine type, maybe I make it even smaller, maybe I make it really quite tiny, just one virtual CPU and 4 gigs of RAM, which I think most of us have laptops, maybe even phones with more power than that. So that's one piece of understanding in terms of the cost, right? You can certainly drive it up and down pretty easily. The other piece of around pricing is training. So AI platform training gives you, let's see, cloud AI platform training. Look at that autocomplete going to work. And so what I can do if you're trying to figure out pricing details is just search pricing. There's usually pretty consistently a pricing page for each of these products. So training has pricing, and then this is actually predictions pricing. I know the pages look very, very similar, but that's how I would look it up. So in training, I don't know what region you're in, whether you're in the Americas, Europe, or Asia Pacific, but you can see there's slightly different pricing depending on where you are at, depending on what kind of machines you're using. It can get a little bit hectic, right? There's a lot to look at with predictions. It's a similar kind of thing. There's batch predictions and online predictions, and they're priced per node hour. And there's actually a pricing calculator. So this is probably the most generic answer to pricing is go to cloud.google.com/products/calculator. And there's a super detailed pricing calculator that you can use across all of GCP's products that you can really specify every detail of what you're going to be pricing out, where it's going to be, how many you want, what type of machine you're going to be using, et cetera, et cetera. And that'll give you a very exact amount, and it's handy to like play around with. So if I can find it, so AI platform used to be called machine learning engine, and it looks like the pricing calculator is still clinging to that old name. So if you're looking for this, what you're looking for is this word. It comes after all of the APIs: translate, vision, cloud, speech, natural language. That's what the NL here stands for, and then machine learning. So I made it a little bit bigger for us here, and we can choose the training. You can choose kind of the pricing tier. So if we do something like custom, now we can say what kind of machines we want, and same with prediction. We can do online or batch, and then number of node hours, and it'll do the model. And what's cool is it'll add it to your estimate, and so you can actually include multiple things in here. Maybe you have this machine learning job, but you also have a compute engine instance, and you want to price in the cost of storage and so on. So that hopefully kind of addresses that question. Let's see, the next question. Let's see which one's. All right. Another question from Dharmesh. As notebook instances are eventually compute, do we expect to see recommendations just like we see on the GCE VM dashboard? Yes. In short, you actually see them even now. I saw it when I clicked into this one, for example. I might have scrolled past it a little bit quickly. I know you see it in the dashboard. You also should see it in the detail view right here. It says this instance is underutilized. You can save an estimated $111 per month by switching to this machine type, and I can just click resize and it'll work. I can also see that in my VM dashboard right here. You can see right here, instance, it's the same instance, TF115, GPU is underutilized, save, and I can go into it and adjust it. So where is that? It's right here. This is a little light bulb moment for us here. So it does, in short. Could I train my model on premises data and deploy to GCP? Absolutely. So this question is an anonymous question, but it's a really good one. You can train your models locally. You can train them locally on your laptop locally, or you can train them in your data center, and then you have that exported model, right? And so you can go over to AI platform and models, and all you'd have to do is upload that model file, that exported model. In TensorFlow, it's the saved model format. With sklearn, it's something you can pickle it, or you can use the joblib library, which will package it up for you. And instead of create model, the create model, this is a terminology thing. Model here refers to really a wrapper around models, right? There's lots, or versions, I should say. A single model has lots of versions inside of it. And so this one only has one, but when we create a new version, we point to that cloud storage URL, and so we could even browse for it and choose from your various buckets and put it in there. And so that allows us to deploy a model without training it on GCP. So it's very flexible in that way. You can choose at what point in the workflow you want to insert. You don't have to use, for example, you don't have to use the data labeling service. You could bring your own data, or you can use the data labeling service, but then do your own training and then deploy it back on GCP. You can kind of completely mix and match however you like. Let's see, we have one. Oh, there's more questions. How is AI Notebook different from Google Colab? From Martin Kodak. Thank you for that question. It is a very good one, and one that's worth considering. Google Colab is free. It is not connected to your GCP account by default, at least. And of course, it has a different UI. It's orange. And those are some of the differences, but I think importantly is for those who are using GCP in a kind of business or enterprise environment, AI platform notebooks give certain guarantees around security and privacy of your notebook, right? Because it's sitting inside of a project, it's secured in a VM, et cetera, and you can have those performant reads from cloud storage, from your Cloud SQL, and whereas Colab is not just free, but the notebook sometimes will time out, right? Because you have your own reserved instance, and the customizability of that VM is an important difference as well. I think that's probably the biggest difference in a lot of ways. AI Platform Notebook, you can choose exactly which GPU you want, how many GPUs you want, or TPUs in that case, and you'll have them, right? It won't be taken away from you. There will be no kind of, oh, that's not available right now. It's stocked out. Too many people are using it. And it won't time out on you. This is also important. For long training sessions, I know a lot of people run into this problem where on Colab, after around 6 hours or so, the notebook will time out, even if it's active. So you might be running a big training job on fine-tuning some ResNet or XLNet, and then it will time out on you. And so that can be problematic, and it defaults to kind of storing its stuff onto Google Drive and writing and reading from that, and that can also be kind of difficult in terms of read performance. A lot of times people say that they feel like Colab's read speeds are slow, and typically the answer is, well, if you read from an actual blob store like cloud storage, then that can fix that for you pretty quickly. Couple of final, we are at time here. Let's see. I also want to just take a peek at the live stream. Mostly just hellos from all over the world, everywhere from the US, from California all the way to the East Coast, as well as it looks like there's people from Istanbul and Colombia, Jersey, Spain, Algeria, India. So that's really exciting. Thanks everybody for joining us. And I guess at this point, we should try switching over to the and I can address the other questions on the Q&A afterwards, perhaps, or if there's a way to do it in the chat. The only other shout out I'll give is for TensorFlow Enterprise. For those who are interested in learning more about that, this Friday on this channel, as in tomorrow, we'll be doing a 1-hour live stream with my colleague Gonzalo, who wrote up a really useful blog post called 10 Ways to Use TensorFlow Enterprise. And we saw some of them today, but there are some really out there ones that I didn't even know existed. And so I'm really excited to kind of interact with him during that. So we'll be live streaming that on this channel 3 p.m. Eastern time, noon Pacific, tomorrow. And other than that, let's see, other things going on the channel would be Sarah, my colleague who's actually presenting right after this. Her and I did a really fun live pairing session a little while back on explainability, and so I'll share those links in the chat.
So before I dive into too much, I want to talk about, show some specific examples of the type of explainability that I'm mostly going to be focusing on today, which is called feature attributions. So feature attributions tell you which features were the most important in signaling your model's prediction. So what does this look like for image models? It looks, feature attributions looks a bit different for every data type that you'll be working with. So for image
Oh, sorry, you're muted again.
okay. Do you know why that? I'm not sure why that keeps happening. That's odd. How long have I been muted again?
Just a second. Don't worry, keep going.
Okay. Yeah, just interrupt if I get muted again. So in this example, it's showing us the top predicted breeds for these animal images. And we can see in red the highest signal pixels highlighted. So here we can see for the bird, it's picking up on the shape of the bird's beak. For the meerkat, it's picking up on the small dark eyes. So in this case, it can help us debug our model, just make sure that verify that it's performing correctly, that it's picking up on the right parts of the image. If instead it was picking up, on something in the background or just random shapes throughout the image, we might want to then go back, revisit our training data, make sure that it's good and that we have enough varied representations across each label. So what does this look like for text models? So I have two different examples here. The top one is a model that's predicting the genre of. Okay, I'm muted again. I don't know why that's happening. If anyone can figure out why, let me know. I'm on now. Okay, so what we get here is this is showing us in blue are the highest signal words. So the words that triggered our model most to predict the genre action in this case. The example on the bottom is more of a sentiment analysis use case. So what in this case, explainability is kind of helping us try to eliminate bias from our model. So if we have a sentiment analysis model, we want to make sure that identity terms don't influence the model's prediction. So an example here, I live in Boston. So if I'm describing myself and say I'm a Red Sox fan, this should yield the same sentiment as I am a Yankees fan, though some may disagree. We want to make sure our model isn't using identity terms for that particular sentiment analysis use case to influence the model's prediction. So you can imagine, how that might play out, with more controversial words in your model. Just an example of how explainability can be useful in identifying and reducing bias. For tabular models, this is pretty straightforward. So this is a model I built that predicts the duration of a bike trip. I'm going to be showing a demo of it shortly. So what we see here is that for each feature, we get an attribution value that tells us how much this particular feature affected the prediction. Negative values mean it pushed the predicted value down. Positive values means that it pushed it up. And the most important features are the ones with the highest magnitude. So we can look at the highest absolute value feature attributions. So that's kind of why it's important for model builders, folks that are debugging models and trying to improve them and understand how they work. Why is this important for end users? So an image example, this is a diabetic retinopathy model that was built by an internal team at Google. So this model predicts and classifies images of eyes and identifies the severity of diabetic retinopathy on those images. So I'll just refer to it as DR since it's kind of a mouthful. It's a disease that affects millions of people around the world. If it's caught early, it can be cured. And so, the goal of this model is to make it easier for medical professionals to diagnose this in an image. So when a doctor sees a model prediction associated with an image, let's say for this example, it was mild DR, it's hard for them to know exactly, why the model predicted that. What explainability can do for us here is it can show us the regions on this image that cause the model to predict mild. So here it's correctly identifying some lesions in the eye, which matches up with this mild prediction. So in this case, whoever is reading the eye image can have a bit more trust in the prediction, knowing why it predicted that. It could also help them identify a faulty model. So one example is, let's say that you have some X-ray images and a bunch of them have annotations, doctor notes on them. Let's say you train a model and accuracy looks good, but it actually is just picking up on those annotations to make the predictions instead of the actual content of the X-ray. So you could use that to then go back, wipe the annotations from the slides and retrain a model. Just one example of how it could be actionable. Recommendation models, fairly obvious. You want to know if you're recommended something, maybe why you were recommended that thing. And then credit score, a financial metric that we use here in the US. When you get a score, it's useful to know, if your score is bad, how you could improve it. If your score is good, why it was good. So some examples of why explainability is important to model end users. So why is explainability important? Here's an example of a model that I trained to 99% accuracy. So some folks might say, okay, 99.3%, that's pretty good. Should we deploy the model, put it in production? Are we ready to go? But accuracy is only actually one piece of the model evaluation picture. It's really important to go a little bit further, especially in certain use cases, to understand why your model is behaving the way it is. In the example I mentioned before, with the annotations on medical images, in that case, if we had just deployed a model with 99% accuracy, that's just an example, then turns out that if we had inspected the model, we would have found that it's not actually picking up on the right things. So that's why explainability is another important addition to accuracy as an evaluation metric. I kind of already touched on this, but just to summarize, it's important to two groups of people. And what explainability does, I have this black box metaphor. Oftentimes, especially deep learning models are kind of a black box. You don't know exactly how they're behaving and how the model is arriving at a specific prediction. So explainability can help uncover that. So for model builders, this can help you understand how your data set is influencing the model output, things like identifying biases. An example of maybe how a data set could influence the output, let's say that you are building a credit scoring model like I showed in the previous slide. and your model seems to be performing well, but it turns out that you have a very small amount of training examples from a specific age demographic. So then when you try to make a prediction on someone that falls into that demographic, your model's prediction may seem accurate, but may not accurately reflect, the real world, how it should. Explainability can kind of help you pick up on things like that. And in the end, it can also help improve model performance. Model end users, two groups of folks here, people that are just getting predictions from your model, but then also people who might need more of a summary of how the model is behaving in aggregate. So things like regulators, auditors, folks like that, non-technical decision makers within an organization. So explainability can take a number of different forms. It's not just something you do once and then you're done. So I wanted to just talk briefly about how it fits into the whole machine learning lifecycle. So here we have a typical ML workflow. Everybody's is a little bit different, but this is just intended to encompass a lot of the important steps. So first, before you even build your model, you can use some tools to look at your data set, understand areas that are imbalanced that you can either correct for by collecting more data, or things that you might need to be aware of when you're training your model to maybe you need to do something like downsampling or upsampling. Once you've built and trained your model, there's some tools you'll use, and I'm going to talk about some of these later on, to make sure that your model is treating different groups of users fairly. You can also do analysis that will help you set prediction thresholds. So what I mean by prediction thresholds is, let's say that I am building a model to identify whether an image contains a cat. Maybe I only care if my model says it's a cat with 80% confidence, maybe that's enough. I'm okay to show the user, yes, it's a cat. Not really like a high stakes use case. So in that case, 80% is my prediction threshold. If I have, a medical use case, on the other hand, I probably want to be closer to 99% confident before I confirm, a positive prediction. So in that case, 99 would be my prediction threshold. And then once you deploy your model, the data that is going to be sent to your model in production is going to be, a little bit different from the data that you use to train and test your model. So it's important to look at these steps again once your model is deployed in production. And then finally, if it makes sense for your use case, you can surface those prediction analysis results to end users. So now that you have kind of an understanding of what explainability is, I want to talk about Explainable AI on Google Cloud and how you can use it today. I'm just going to see if there's any questions in the chat real quick. No, looks like nothing yet. So yeah, in the Meet chat, just pop questions if you had them. So Explainable AI is a relatively new product on Google Cloud. It launched last November. And Explainable AI is an umbrella term that refers to explainability functionality that we have in right now 2 different products on Google Cloud. So I like to represent all of our different products in this pyramid organized by levels of abstraction. So the products towards the bottom, frameworks isn't really a product, but these 3, which Yufeng covered in his presentation, are most of them. These are products that are targeted more towards machine learning engineers, data scientists, folks that have a bit more of a machine learning background. The top half of the pyramid is targeted to folks that maybe want an easy way to add machine learning to their app, but don't have as much of an ML background. So maybe more like application developers, data analysts, things like that. So right now, explainability is available in 2 products. First is AI platform prediction. Yufeng did a great job covering that, so I won't go into the details, but the way it works with explainability is you deploy your TensorFlow model to AI platform prediction. You don't need to train it on GCP or AI platform training. You can train it wherever you'd like. You deploy it to AI platform prediction. You provide a JSON data file that gives some information to the explainability service. And then when you get predictions on your model, you get these attribution values back that tell you how much a particular feature influenced the prediction. And then AutoML is a product that lets you train and serve custom models without requiring you to write any model code at all. AutoML has a bunch of different variants for different data types. So there's AutoML vision for images, text, translation, video, and finally tables for tabular data. So explainability is also currently available in AutoML tables. So the way this works is when you train a tabular model in AutoML tables, you automatically have some explainability features available once your model is deployed. So you can see both global level explainability, which features overall across your test set were most important to the model, and then you can also get instance level predictions. So brief overview of the products it's available in, and now we're going to get a little bit more into the details, and then I will go into some demos. So this is what explanations looks like on AutoML tables. This is that bike distance, trip distance prediction model that I talked about that I'll demo shortly. So here we see global level feature importance on the top right. This is telling us Euclidean is a distance feature. It's telling us which features are most important overall. Looks like we have a question in the chat. One sec. Yes, it's currently only available for TensorFlow models. I'll talk about that a bit more in a couple slides, but good question. The question was on if explainability is available for other frameworks. At the moment, just TensorFlow for AI platform. So this is our global level feature importance. We also get instance level features. So if we send a single example to the for prediction, we get feature attribution values for all the different features in our model. And this is available, I'm showing here in the UI, but you can also get this in the API so that, you know, when you're making predictions, maybe on a web application, for example, you can get these feature attribution values back and do whatever you'd like with them. So that's a brief summary of how it works in AutoML tables. How it works on AI platform is you build your model in TensorFlow, whether it's tabular, text, or image model. You deploy it to AI platform and you specify which explanation method you want to use. I'll talk about that in a moment as well. And so what we're seeing here is an example of an image model and the explanations you get back. Right now, we have two different explanation methods that are available for images. We just added this new one, which is, you can see on the right. So what we see here is an image of a husky. On the left is the original image. In the middle is a explanation method called integrated gradients, which is a pixel level attribution method. And then on the right is one called X-ray, which is new. We just launched that last week, I believe. And this gives you more region level explanations. And so you can see the scale here. So regions that are highlighted in yellow were most important to your model. Darker blue, purple regions were least important. So what we typically recommend is integrated gradients. The one in the middle is better for what we call non-natural images. So images maybe taken in a lab, medical images, maybe visual inspection images. If you have a model that takes images from an assembly line and tries to find defective products, that would be a good use case. Natural images, kind of like the one of this dog, you know, things taken in the wild, outside, around the house. This is typically a better use case for X-ray, spelled XRAI. I have a slide on it in a moment. As you can see here, because in this case, we kind of just want a generalization, like looks like, you know, the shape around the nose and the cheeks of the dog were the most important to the model. We don't really need like pixel by pixel attributions, but again, it depends on your use case. So another thing to note is explanations on AI platform has an integration with an open source tool called the What If tool. So What If tool is developed by a team at Google called the PAIR team. And it's a tool for inspecting your models, understanding how they're behaving. It works on any model type, not just TensorFlow models. And your model doesn't have to be deployed to AI platform to use it. You can connect it to a model that's using TF serving. You can just pass it a local model if you're running within a Jupyter notebook. But they did add some cool features that integrate directly with models deployed on AI platform, and specifically models deployed with explanations. So if you do choose to connect it to your AI platform model, I'll show you an example of this shortly. You can see all of the attribution values for your model, and you can also make some cool custom visualizations with that information. So this is the workflow for deploying a model on AI platform with explanations. So you build your model just the same as you normally would. You deploy your model to AI platform with G-Cloud or the AI platform API. When you do this, as Yufeng mentioned, you put your saved model assets into a cloud storage bucket. For explanations, you need to add one more thing. You need to add a JSON file that provides some metadata to the explanation service. And then once your model is deployed, you can use it instead of calling predict on your model, you would call the explain method with the AI platform prediction API. And then you can analyze those responses in a notebook. You can also use the what if tool if you want to integrate that way. So yes, so I mentioned 3 different explanation methods. These are all based on publicly available research. So for images, we have both integrated gradients and X-ray. The links to the papers, if you want to check out more, are available here. And I can also share those out at the end. So integrated gradients and X-ray were both developed by teams at Google. Sampled Shapley is an approach that's been around for a while. If any of you have tried out the open source framework SHAP, it's a great explainability framework. Definitely recommend trying it out if you're new to explanations. They have some great docs and examples on their GitHub repo. So the version of Sampled Shapley that we've implemented on AI platform is similar to the one that's used in that framework SHAP. So with that, I'm going to go to a demo, just making sure you can all still hear me. Looks like you can. Okay. So first, I'm going to show AutoML tables. So this is the bike model that I mentioned before, using some data about a bike trip to predict how long the trip took. This model, my teammate Amy and I worked on together. So what we did was we took some publicly available data from BigQuery public data sets, data on public bike share trips in London, and then we joined that with some NOAA weather data. It's another BigQuery data set. It's publicly available. If you want to check it out, anybody can query that data. So we joined the bike data with the weather data to see if we could detect how long a trip would take based on some information about the trip, like location and weather, things like that. So when you upload your data to AutoML tables, it will infer the data type. As you can see here, it gives you some stats on your data. You can choose the target column. That's the thing you're predicting. In this case, it's duration. And then over here, if we go to the Evaluate tab, we get this nice feature importance visualization here. So here we can see what AutoML tables does is it takes the data in our test set and it automatically splits your data for you unless you specify. So you just upload your data set. Number of ways to do that. It'll split your data into train and test sets. And then it takes your data from the test set and uses that to create a summary of overall feature importance for this model. So here we can see that distance of the trip was the most important feature. It kind of makes sense. Followed by day of the week, location, a couple other things. Max refers to max temperature for the day. Another thing that you can do, so this was global level feature importance, is AutoML tables also lets you try out predictions right in the UI. So here it'll just populate some random feature values for you for the different features if you're using it in the UI. Obviously, if you have a lot of features in your model, you probably don't want to always get predictions through the UI, but just a demo. If you check this generate feature importance checkbox, and then when you make your prediction, you should see feature importance values here. So here we can see that distance caused the model's prediction to increase. I think this model is predicting in seconds, not minutes. The demo that I'm going to show in a moment is predicting minutes. So this caused the prediction to increase. Location cross, which is a feature that kind of represents latitude, longitude, caused the model's predicted duration to decrease. So you may be wondering, like I'm saying that, particular features cause prediction to increase or decrease, but from what? What is that relative to? So that is all relative to what's called the baseline prediction for your model. And when you use explainability in AutoML tables, it sets the baseline for you. I believe what it does is it just takes the median across all of your feature values and uses that as the baseline. So what the baseline prediction means is for that median, in that case, what does your model predict for the median across all your feature values? So the baseline prediction is going to be the same for every single prediction you send your model. So it uses the baseline to determine the feature importance. So when I say that distance caused the prediction to increase, it pushed the model's prediction up this amount from the baseline. I'll talk about baseline a bit more after I show the AI platform demo. So you don't set the baseline in AutoML tables. You don't have to worry about that. In AI platform, when you deploy your model, you do set the baseline. And so you have some control over different baseline values. It's an important concept, and we have a white paper that's been published by the team that explains it in a bit more detail, but the baseline can really influence the quality of your explanations when you're working with models on AI platform. So now that you've seen a preview of how it works in AutoML tables, I'm going to show you a demo in AI platform. I want to make sure I leave time for questions, so I'm going to go through this kind of quickly. So Yufeng already talked about AI platform notebooks. I'm just running an AI platform notebook instance here, and so this is where I'm going to run the AI platform demo. So first I'm going to show you an image example. And so what I have here is, let me just make sure that, yes, okay, people can still hear me. What I have here is a model that does some basic flower classification. These are the 5 different possible classes. So here we see what the model predicted without explanations. Pretty self-explanatory, predicted these flowers correctly. And now we're going to visualize the explanations first with integrated gradients, and then I'll show you X-ray. So integrated gradients shows us which pixels the model thought were most important when predicting both of these classes. So this is kind of helping us see that, yes, the model is actually picking up on the shapes of these flowers and is understanding, the shapes that are specific to a dandelion and a daisy. We'll make the same request. I've deployed a different version of the model with X-ray. So when you deploy a model version, you specify the explanation method. You can only have one explanation method per model version. So I'm now pinging a different version. I'm using G-Cloud. And yeah, it turns out in this case, I think personally, X-ray is a bit better for the flower use case because it really pops. I can see right away which areas were most important to the model. And then one more example, this isn't a model that I'm going to query live, but I have a preloaded image to show you how our explanation service works with the diabetic retinopathy model. So here we have an image of proliferative DR, diabetic retinopathy, which is the worst form. Our model classifies it correctly, but the explanations really help us see the exact areas of this image that caused the model to predict proliferative DR. I did verify with a medical professional that these were the correct areas of the image to pick up on. So that's a preview of how it works on image data. And next I want to show you a demo of how it works on tabular data. This model is doing the same thing as the bike prediction model I showed in AutoML tables. The features are slightly different. So I'll show you the data we're working with. So these are all of the features for the model, and we're using this to predict trip duration. So now I'm going to show you just one example from the data set. So here's all the feature values. The predicted trip duration is 11 minutes. So we'll send it to our model. We'll compare its prediction with the ground truth, which is 11. So here we see our model got pretty close, 10.71 compared to 11. That is sort of useful, but again, we really want to kind of dig deeper than that and understand why our model predicted 10.71. So here I'm going to show you the attribution values. So here for this model, the baseline prediction is 13.6. I use the median as the baseline here. I could have used something else, but I chose to use the median since that made sense for this type of data. So here we can see that the distance in this case caused the model's prediction to decrease by 2.5 minutes, which makes sense. So the predicted trip duration is less than the baseline by about 3. So we should see mostly negative attribution values here, which we do. Start hour was the next most important feature. So this is handy, but it would be nice if there was better way to visualize those attribution values, which is where the what if tool comes in really handy. So the what if tool works by you connect it to a Cloud AI platform model. You pass it some test data. So I've sent it 500 examples from our test set. And that's what it's visualizing here. So across this axis here, we just see the predicted trip duration on the x-axis for all of these different values. There's nothing on this axis, it's just spreading out the values since there's a lot of them so that we can see them all. There's lots of really cool stuff you can do here. So you can click on individual data points to see the values for those features. We also get, because this is an AI platform model, deployed with explanations, we can also visualize see those attribution values here. So what I could do for this one, another thing the what if tool lets you do is you can change the feature values and rerun prediction. So here we can see the actual duration is 19 minutes. The model predicted 21.9, pretty close. But let's say I change the temperature to 10. This is in Celsius, by the way. I can rerun the prediction and see, okay, that caused the trip to be about 2 minutes shorter. So I can see how each feature affected the prediction. Because the attribution value for distance is much higher, I would expect that, you know, if I cut the distance to 1,000, the predicted duration decreases by a lot, which kind of makes sense because that matches up with the attribution value. There's lots you can do with the what if tool. So this chart region over here is all customizable. So let's say I wanted to color them by inference error. And we can see a legend here. You can create all sorts of custom charts. Sorry, I'm having trouble scrolling, but you get the idea. You can color them by, or you know, change the x-axis to be attribution value. So you can create some really interesting charts based on that. There's a couple of other tabs here. So what the features tab does is it just lets you see a distribution of the data that you sent the model to make sure that the data you've sent it is balanced. One thing to note, you can use the what if tool without even connecting it to a model. You'll just see this one tab right here. So if you want to just pass it a data set and see like how that data set is balanced, do some visualization, you can do that and you'll get this view. So that is the what if tool. I'm gonna pause and go to questions. See if there's anything in here. Oh, please zoom a bit. Sorry about that. I don't know if that was related to the image example or the what if tool. I can try to zoom in a bit more here. So you can see everything there. This other question was, I'm going to go back to Mohit's question about explainability. It's only available for TensorFlow models. Yes, that is currently the case. The current product works with models that are deployed, built with TensorFlow 1, working on adding more support, obviously, for TensorFlow 2, along with other frameworks. If there are other frameworks that you're using that you would especially like to see with explanations, please let me know. Just drop it in the chat. If you have more questions, also feel free to find me on Twitter. I'm srobtweets. Here, I'll skip to the, since we're getting close to out of time. We have about 10 minutes left. So I want to make sure we have time for if there's any more questions, and Carl's presentation afterwards. I'll skip ahead to this resources slide. But yeah, if you have any questions, you can DM me on Twitter. We can connect over email. Would love to hear if there's a use case that I didn't talk about that you'd like to see covered by explanations, which frameworks you're using. I think you may have also been asking about the different explanation methods. So right now, those are the only three we have. We're focused more on, improving the usability of the tool, adding more functionality that way, versus adding more explanation methods, since we have 3 already. But if there's other research out there that you would like us to see, we love to hear about it. So let us know if there's other things you'd like to see covered. Do we get the notes or slides later? I can work with Emilio to send you a PDF of the slides. Would be happy to send out the slides. Good question. Since we have a bit more time, I will just briefly talk about the concept of baseline, since I brought that up and didn't really go too much into it. So just a quick side note on baseline. And if you have more questions, just drop them in the chat and I can skip back to it. So I talked about how all the feature attribution values are relative to your model's baseline. And at its core, explanation seeks to help you answer this question. You know, why did X happen? X could be, why did the model say this is a cat? Why did I get rejected from this loan? Why did this transaction get flagged as fraud? The baseline is this Y value here. So when you're explaining something, you're essentially saying, why did X happen instead of something else that should have happened? Y is your baseline. We have this concept in explanations of uninformative versus informative baselines. The baselines that I showed you in all the examples so far are all uninformative baselines. What I mean by that is we're just using the median across our entire data set. It's not based on a specific question that we're trying to answer. Same with image models. Image models commonly use uninformative baselines, typically a solid black or solid white image, or an image of just random pixel values. Obviously, if your image has a lot of black or white in it, that's probably not going to be a good baseline, at least the solid image. The random one might be better. But there are certain use cases where we want to use an informative baseline. So one example of that, and I have a whole blog post in CodeLab on this, is fraud detection. So if I'm building a model to identify fraudulent transactions, I care most about understanding why the model predicted fraud. Why, for the transactions it flagged as fraud, why did it do that? I care less about transactions that it doesn't think are fraudulent. So in this case, for the baseline, for this model that I built, I used the non-fraudulent transactions as the baseline. So I took the median value across all of the non-fraud examples, used that as the baseline, and then use that to explain the fraudulent predictions. You can experiment with different baselines. So you might wonder, like, what if I want to explain the model's predictions on transactions that weren't fraudulent, especially to understand why it got those wrong? You could absolutely deploy another version with a different baseline and compare the results between them. So just a quick note on baselines, just to help you understand them a bit more. I'm going to jump back to this slide just to share some resources since we're getting close to time, and then I'll hand it over to Carl. I have a step-by-step code lab on the fraud detection use case that I just briefly touched on. There's some sample notebooks to show you how to deploy image and tabular models to explainability on GitHub at this link. The white paper is really great. Would recommend that if you want to learn more just about the theory behind explainability, why we chose some of the explanation methods that we did, and how to think more about choosing a baseline. And then if you're interested in the what if tool, they have a lot of great demos here. So with that, I will check once more for questions. Sorry that my question thingy didn't work. I will fix that for the next time. With that, I'm going to hand it over to Carl.
All right, thanks, Sarah. Great job. I will take over from here. Sorry. There we go. All right, can everybody see my screen? I'm not hearing audio, so one second, let me just check.
Yes.
Yeah.
Perfect. Okay, thank you. Awesome. All right, let's dive in. So hey everyone, I'm Carl Weinmeister on the same team as Sarah and Yufeng, and I'm going to talk about a, I guess you could say, a workflow of how do you use the cloud AI platform tools to solve a certain kind of AI problem, which is time series forecasting. So we'll talk a little bit about the tools and how they're used, but we'll also talk about the theory of time series, and hopefully you come away from the session learning a thing or two, and we'll show a demo at the end and answer any questions you have. So with that, let's talk about the agenda. We'll talk about some of the challenges of forecasting. I'm hearing a couple of beeps, so I'm just going to check in case there's any. Oh, so we'll check those questions later. Yeah, so challenges with forecasting. Just overall, how is time series data different from other kinds of data that you might be working with? How to model it, a little bit about the tooling, and then a demo. So why is forecasting interesting? It's really something that humans have been trying to do since the beginning of time, right? Predict the future. So it's a very common problem, has a lot of value, and it's difficult, right? It's predicting the future. So, you know, I want to talk about, you know, here's a little bit more information from a McKinsey study that talks about the various types of data and the value that you can get out of solving problems with AI with that kind of data. And you see that, you know, structured and time series data are by far a couple of the areas that in the business world you can have the most impact. So really a kind of an untapped area to apply AI, solve all kinds of interesting problems. So let's start with discussing some of the challenges in time series forecasting. So let's first talk about classical forecasting methods. So in this presentation, I'm not just going to talk about machine learning because it's important to say, let's look at what already exists. How does machine learning improve on what's already exists? Because there are some techniques out there that are, you know, have been used for years and are very valuable. So first on this slide, we're looking at what's called univariate time series problems, or looking at one variable in the data. And so what can the classical or statistical models do well today? One, we'll go left to right here, is giving you a probability distribution, right? So looking at, here's my prediction, and here's a range of possible values and confidence levels from that. Another area is looking at seasonality and holidays, being able to understand where those might fall in the trends. Another area is inferring outliers and shifts, right? So given that, you know, the first point, we have a probability distribution of our forecast, we can say we expect the value to be, say, within a 95% confidence interval between these values. That allows you to easily detect, you know, when you're outside of those bands and flag something as an anomaly. Another thing that's handled well is seasonality, and even multiple seasonality. So when you think about seasonality, or this sort of repeated cycle in your data, there can be multiple layers of it, right? There can be, say, it's a call center. Maybe on Mondays you have high call volume because there's some pent-up demand over the weekend. People are calling on Monday. So that's sort of a weekly layer of seasonality. You might also see, say at a monthly level, some seasonality where certain times of the year are slower than others, and so on and so forth. So you can decompose the different layers of your model to look at those aspects of seasonality. So these are things that machine learning could also do well, but just wanted to kind of talk about, you know, where we are today and how the existing tools can handle that. Now, neural networks and machine learning can improve on some of those existing techniques in these ways. So one is multiple time series. So imagine that you have problems you're trying to solve where you have multiple items that you're tracking in parallel. So maybe, and that are related. So maybe it's something like in a retail store, you have different items that you're selling, you know, and you're tracking their purchases all together. And a traditional statistical model would sort of model each variable separately. And you don't get that interplay between the different variables, because maybe there's a scenario where the consumer has a fixed budget, and you know, if they buy one item, they might buy less of another item. And so those kinds of relationships wouldn't be captured by the statistical model, but a neural network would be able to discover them through its process of training and reducing error and finding the right answer. Another area where ML can shine in this type of problem is around a cold start. In other words, where there's not a lot of data to make a prediction from. Not an ideal situation, but it's quite common where you say, hey, given what we know, what can we tell, even if it's not a perfect answer. And some of the statistical models benefit from multiple cycles of information to be able to get to good answers. Neural networks also can handle noisy and sparse data sets, gaps in time series, things of that nature. And finally, rich metadata. So another neat thing about neural networks is that not only can you track a variable, but maybe some metadata around that. So maybe you're tracking things like temperature over time. Maybe you want to add some additional things like the geolocation of where that temperature was taken as an additional variable in your model. Maybe that will help improve your accuracy. Maybe it won't, maybe you'll start overfitting to that, but that's an example of where you can add additional metadata and your neural network can possibly improve from that. Some other ways that neural networks can improve on this is predicting multiple time steps ahead, fewer retraining runs. So the model that you create, the ML model that you create, is more stable. Once you train it, it will decay into the future a little bit less. It will last a little bit longer and still have some power, whereas some of the statistical models need to be retrained, and it's pretty computationally expensive to do that. And finally, there's beginning to be a lot of great ML infrastructure and pipelines that you can take advantage of building it in this way. Yufeng talked about that earlier today, and the pipelines and all the different cloud-based tools that you can take advantage of with the ML approach. So one industry example here, and there's many of these. It's an example of energy forecasting, right? So we're looking at, example of predicting. Sorry, I'm hearing a question. Or okay, I'm not sure what that was. Okay, so let me keep going. Yeah, so here's an example of predicting a wind power output, right? So looking at temperature, and this is where, you can read this blog about it. If you can predict how much power output you're going to have, then you can commit to the power grid about how much, what that's going to be. That can add a lot of value. And some of the challenges with this problem play well into the machine learning approach, predicting multiple time steps ahead, multiple exogenous variables, so including data outside of just the variable you're trying to predict, so temperature and things like that, and then noisy data sets, so IoT data where there's sensors that go bad and gaps in the data and things of that nature, so handling that kind of noisiness. So this is just a good example of pulling all those attributes together for a good machine learning model for forecasting. So now we've introduced some of the challenges. Let's now talk more about time series as a whole. So if you're a little bit new to this field, what really is it? So it's a data set that has two pieces, time as an independent variable, and then whatever you're measuring is the dependent variable. And so this is an example of a univariate problem, right? We're tracking one thing, you could have multiple variables here. The key is that you have time, and then you're trying to see that relationship between that variable and time. And when you look at a time series, say you start at the very top of this diagram, that's what it starts to look like, in the beginning, and then you can apply some techniques to decompose these different layers. Like one might be a trend, kind of over time, what's happening, the seasonality, and then finally, what you're left with the residuals. So kind of the randomness or what's not explained by the trend or seasonal components. And ideally, you'd want that residual to be close to zero, the variance to be kind of small. And this is where your ML model is going to look at maybe there's some additional features that will help kind of reduce those errors that you see at the very bottom. So that's kind of the componentized view of it. Now let's talk a little bit about the foundation of machine learning and how this applies to time series. So a key assumption in modeling is your data is IID, that's independent and identically distributed. So meaning like in a coin flip example, each time you do a coin flip, it's independent of the previous time. And each coin flip has an identical probability distribution. In other words, it's governed by the same rules of a 50-50 distribution every time. So is time series data following those IID principles? Sometimes, sometimes not. So let's look at what we can do to adjust the data so that it can be used in machine learning problems. Okay, so the data that you want to apply to a machine learning problem means should be stationary. So stationarity means that over time, the statistical properties of that series don't change. So the mean stays constant, the variance stays constant. You don't see all these different statistical factors aren't a function of time. So if you do see like a time series like this that exhibits those factors, there are some different techniques you can use, right? So one might be detrending. So you take that series and you apply a linear regression to it, and you remove that trend component to basically straighten it out. And so it has a mean of 0. So that's what you see below. That may not be enough. Maybe you need to do something like differencing, so that here's an example where you might subtract last year's value from this year to kind of get rid of those differences, and that will take another layer out of the seasonality out of the equation, right? So typically the statistical methods are going to require that stationary data. Neural networks can use non-stationary data in some cases, but there's papers that show that pre-processing the data like this can improve accuracy in some cases. All right, so talked a little bit about the theory. Now let's dive into, if I actually have some raw data, how do I transform it to use it for supervised learning that you may be familiar with? So say on the left, we have a bunch of observed values for each month. Then what we would do on the right side here is create lagged variables. So if we're trying to predict the column on the right, the actual recorded value, we might say go 1 month back, t-1, another month back, t-2, and so on and so forth. And that is what we would use to predict the column on the right. So it takes a little bit of data pre-processing to get to that point. And you might have other variables, right, that you're tracking that you'd include in this as well, and different lags of those. It's important to keep in mind, typically in machine learning, you do this split of your data. You train on part of the data, and then you hold out part of the data to test and evaluate the accuracy. Of course, you don't want to test on the same data that you're training on. That's, cheating, that you're going to have a higher accuracy than what you'd see in real life. Similar concept applies to time series problems, but you need to be even more careful that the way you split the data should be chronologically, that you don't want to use data that's kind of in the future while you're training the model. So you split the test data out kind of to the right, the most recent data. And you can apply some, get more fancy with that. There's concepts like cross-validation machine learning, where you split up your data into different configurations. Like in the last chart, I showed just kind of a random split, but we could do things like, the first fourth we hold out, then the second fourth we hold out, and so forth. That's what you see on the left side here. From a time series perspective, you can't do that. Again, you need to have your test data be the most recent data, but you can break it up in different ways to get better accuracy estimates. Okay, so now we've talked about that. Let's get into the theory of time series models. So let's start with one slide on the statistical models, just to kind of level set, what we're comparing against, because really it's important to have this baseline of how your machine learning model is doing relative to what else is out there. So you may hear of ARIMA as a common approach for talking about these problems. And so just walk through very briefly these concepts. So the ARIMA consists of 3 components. So let's walk through a simpler version of that called ARMA first. So it has 2 pieces, autoregressive and a moving average, right? So the autoregressive piece is you just look at variables from the past, those lagged variables. If you remember that chart that I came up with that showed 1 period back and 2 periods back, and you do a regression and you find out these coefficients that you see here, and you basically try to predict the next value with that. Then you also have a moving average component, the MA, and that's where you can, you start with the mean, but then you basically look at the error that you had using that mean to the past value, and you apply a coefficient to that as well. And then you look at the error, 2 lags before, and so on and so forth, to come up with that moving average piece. So the ARMA model kind of combines both of those approaches together. ARIMA adds the integrated piece. So this is where we talk about statistical models. Usually, I think someone needs to go on mute. Can somebody mute? Thank you. The ARIMA models have that integrated differencing, right? So we're trying to get back to a stationary model. Finally, a more complicated version of this is called SARIMA, where we do a seasonal model that adds an additional sort of seasonality, reduction piece of it. So that's kind of how those work. I've got some notebooks and things that can show that, but that's really not the focus today. But just wanted to do a very quick introduction to that. So with neural networks, there are a couple approaches that have shown very promising results. I'll walk through a couple today: LSTMs and CNNs. They're using neural networks. If you're a little bit new to this topic, what you see here on the right is a simple representation of that, where you take various inputs. You may have one hidden layer, multiple hidden layers, and in this case, we have just one output we're trying to produce, like one value. It could be a price, it could be anything that's just a numeric value that we're spitting out at the end. And so what we do is we go through these training passes, where we have some initial weights that we apply to each of these nodes, and in a bias term that basically another value. And we go through this network, we see what the error is, and then we refresh those weights and biases and continuously adjust them until we learn what the configuration is with the lowest error. So there's a couple of variants of those neural network models that we'll talk about. This isn't a comprehensive list. There's a seek-to-seek, encoder, decoder models, some other things that have also been popular. But I also wanted to point out that you can combine some of these models together. So a CNN LSTM can be popular, and you can even do things like create an ensemble or a combined model where, say, you take the average of the result from a statistical model and combine it with a machine learning model approach, and you might get higher accuracy, higher complexity to do that. But if accuracy is key, then that can be a way to go. So let's walk through what a recurrent neural network is. So a lot of these concepts, are used in natural language processing, right? And there's a lot of similarities in the worlds of time series forecasting and NLP, right? Where in recurrent neural networks, say you might be looking at a string of words in a sentence and trying to predict what the next one is. So a recurrent neural network, the key concept here is that you also see you have that loop on the left side. You have a hidden layer, basically the internals of that node that you are then passing to the next node. So not only are you getting a new value, but you're getting information from the past. So that's where you look you have this sort of look back of, say in terms of words, let me look back a few words and have some context to the next input that I'm getting, and combining all that information together to make my next prediction. So in the world of time series forecasting, something similar, you have previous values and the information about those that are passed in that hidden state along with the next value, and then you're printing out or producing the output that you see there at the top. So the field has evolved, over the past years, and there's been a improvement on RNNs called LSTM, and there's several different variants of those. We'll just kind of cover a quick example that improve on the performance of the RNN. So the key concept here with LSTM, or long short-term memory, there's a couple things. One is it is a concept of remembering or forgetting different things. So this is key, right? So the problem with RNNs is that they don't remember very far back. They start to kind of, they can only really handle short sequences. And they have this problem that's known as a vanishing gradients problem, where you sort of combine these different nodes together, like if we did here, and there's this sort of multiplicative effect where each node, if there's a decay to the information, they keep multiplying. And if that's sort of a number that's close to zero, that signal gets lost quickly. So the LSTM, if you kind of look, we won't go into a ton of detail here. You look at the top arrow there, the cell state, it's multiplying some things together. You see with the X, then you're adding some values together. So the additive nature of the LSTM means that the values are going to be more stable as you combine several of these together. So that's point number one. Point number two is the activation functions are important. So that, the activation functions are applied to the values and transform them. You see the sigmoid one I'm showing here on the right side. The key here is that it ranges between 0 and 1. So you're taking information from past states and you're learning, what any value between 0 and 1 is applied to that information. If you're closer to 1, you're trying to remember as much as you can from that past state. If it's closer to 0, you're trying to forget that information. So you kind of have a better, signal to noise ratio. And you can see that sigmoid activation function that applies that 0 to 1 transformation is applied to several different points in the unit. So you see these, they're called, forget gates and things like that. So, so in all, the benefit of this approach is that the information is more stable, flowing through the sequence is better, and it's better at remembering what's important. So LSTM is a very common approach when we're applying this RNN, recurrent neural network-based model. The second way of learning that we're going to talk about is with convolutional neural networks, or CNNs. And these are typically used for image processing, but they've been found to be very useful for forecasting as well. In a whole bunch of other domains you might not expect that they're as useful as they are. So let's actually look at the picture here on the right as just a starting point. So this is what you would typically see with image data, where you have a matrix of pixels, right? Your height and width, and a filter, that square that you see in the top left is convolved or passed around through that whole image, and it's extracting bits of information, and by doing that, you're capturing there might be slight differences between different pictures, shading differences, the pictures rotated a little bit. By using these windows and then doing a little bit of what's called dimensionality reduction, kind of making things a little smoother, you don't sort of over memorize the details, but you get the gist of what's in that filter, right? And so you learn using those filters. On the left side, it's similar. We're just using one-dimensional CNN. So here again, the similarity between natural language processing and time series forecasting. Here we have a sequence of words, and you only have one thing you control, which is the height, right? And the height is essentially how many items in the sequence you're using, right? So you take this window and, you could make it 2 words, 3 words, 4 words, whatever. Just like, we're talking about time series, how many data points back you want to go. And then you slide it across, and what happens is you start learning kind of these mini patterns in the data of when things kind of start to go down, when they're going to start going back up again. That's kind of the intuition there. And then, it will learn those trends and then apply that to new data. So that's the CNN approach. All right, so let's switch gears. We kind of talked about the foundation of time series problems. Now let's look at how some of the tools can help. Yufeng and Sarah did a fantastic job covering the overall platform and explainability. So I'm just going to briefly introduce the products because we talked about that earlier in the session. The tools that we're going to see today are one, BigQuery. That's a operational data warehouse where you're going to see, or analytical data warehouse where you're going to see how to run massive queries and kind of condense the data into a time series problem. AI platform notebooks, where we're going to create the model, and then showing the training and prediction services. And so we covered this a bit earlier today, but in a nutshell, this is the AI platform where you've got the core and components, the core being your data science and machine learning tools for everything you need to do in terms of ML on the cloud, and then components where you're not necessarily needing to build a model. You might want or a custom model. You could build one with AutoML, or you could use one of the APIs for certain tasks. So AI platform combines that all together. Okay, so with that, I'm going to switch over to a demo. So the first thing I'm going to show is the BigQuery public data sets. Sarah mentioned this a little bit. This is an example of retail. It's the state of Iowa publishes all of the wholesale liquor purchases. So, kind of a random data set. If you can imagine, it's not very common that retailers are going to publish all of their sales transactions publicly and things like that. So this is a good example that gives you that kind of real world data that's publicly available. So, in BigQuery, you see a whole bunch of great public data sets that you can work with. So all I have to do here, I'm going to click to view the data set, and we will just kind of look at what's in the data. Any BigQuery public data set, you're going to see the description of it. You can see information about the schema, each different field, other details, how many rows, and then a preview. And it's pretty straightforward. If you want to query the table, using common SQL commands, you can run those queries, then save the data, create views, so on and so forth. So here is the data we're going to work with. Again, each row is a transaction from a store, its address, the type of liquor, dollars sold, so on and so forth. Okay, so that's our starting point. So we have to do a little transformation here, right? So these are just point by point transactions. We need to say on a given day or given month, what are all the sales? We need to aggregate that. So now let's go to AI platform notebooks, and let's look at a notebook that explores some of these concepts. Okay, so here I am
Hey,
in.
Carl. Hey, Carl,
Yes.
can you please zoom in a little bit?
Sure.
Thank you.
Can you see a little better now?
Yeah, if you can do just a little bit, that would be, yeah, perfect. Thank you.
Okay, absolutely. Yeah, thanks for the early heads up here. Okay. So here is the notebook. It is not yet public. I'm working on this. So, and I have some contact information later, if you want to get in touch with me and have more specific questions. let's kind of walk through this model. So if you're new to this, this is a Jupyter notebook. This is kind of the notepad for data scientists. I'm not going to walk through all the details, but we might need to install a couple extra packages, import some things, connect to our Google Cloud project, so on and so forth. I'm just going to run some of these initial setup steps, and then let's get into the fun stuff. So first, let's run a query here to select 5 records from the data set, just to sample it, right? So here we go, again, similar to what you saw in the BigQuery interface, the different transactions. Okay, great. All right, now let's aggregate the sales by month. So this is, not the ideal query. I completely realize that, where I'm aggregating the different liquor by types using kind of a free text search. If you look at the category, the reason I did that is because each of these categories is very specific. Okay, it just shows the ellipsis here, so we can't see. There's hundreds of categories. So I was kind of briefly trying to just put it into about 10 categories that were understandable, right? So, so let's run this query. What it's going to do is group the different types of liquors and then put them into a monthly view. So let's look at that. Very good. Okay, so we just, we do .head here, which shows you the top 5 rows. We have a given type of liquor, the amount of sales for a given month. Great. Okay, so that's pretty cool. Let's keep moving forward. Now let's look at this overall across all time and sort it. So we see that vodka was most popular, then whiskey, rum, and so on and so forth. Now let's look at trends. Okay, so this is a time series discussion. So let's pick 3 different types of liquors and kind of look at what those trends look like over time. So whiskey, vodka, and rum are what we're going to look at. All right, so what do we see here? Some, I think, pretty interesting trends, right? So you see that vodka and whiskey seem to be increasing over time. So they've got a positive trend, whereas rum seems to be flat over time. So it's not growing relative to the other liquor products. What else do you see here in terms of seasonality? You might notice that it looks like in the summers, generally the vodka rises and then whiskey seems to dip in the summers. And it usually seems like, I believe this is October and December, where there's this constant sort of spike. There's maybe some holiday effect there. I'm not sure why November seems to dip, but whiskey really seems to be popular later in the year. So, pretty interesting. Once you start to separate the data, you're going to see more detailed trends there. So now let's group by day. Okay, so I'm going to now combine the data together. So for the analysis in this workbook, we've kind of done the fun stuff of kind of looking at the individual liquor types. Let's now just do some overall, like liquor sales as a whole. So I've combined it back all together by month and provide some statistics. Now let's plot the data. Okay, so what do you see here? You see this positive trend and this common the seasonality across each of the months. And let's do a few plots here. So this is a box plot, and what that does is show you the line in the middle is the mean value, or it could be median. I don't recall it. These are the 75th and 25th percentiles, and then the max and mid values. So in one view, you see the range of the data. And so this confirms what we were seeing in the charts, where we had October and December being popular months, and a bit of a dip, but still this increase over the year. And then for whatever reason, at the beginning of the year, sales kind of go down again, and then they trend upwards. Okay. So using a package to decompose the elements, we have the seasonal decompose method that I imported before. Here's where we're breaking that into its pieces. So you see a nice even trend, and then you see this seasonality aspect to it. So you can kind of see how those play together. And that's it for the monthly data. Now let's look at some daily data. I'm just going to zip through this. Doing some queries. And let's just show how you might need to manipulate some of the data, right? So in this case, the data set for weekends, it shows NaN or not a number. So it's missing the data. So what we're going to do is we're going to fill that in with zeros. And let's keep going. Let's plot the data. And now let's show how would we handle outliers. So actually, sorry, I'm going to catch that in a second. Let's look at seasonality on a weekly basis. So remember, we were doing monthly data. Now we're showing daily data, and you see a similar thing where no sales over the weekends. This is wholesale purchases again. So this is the liquor stores purchasing from the liquor companies. And so no purchases on the weekends generally, and then this sort of pattern that's sort of persistent over each week. And some more plots, and then I'll do another box plot that again showing similar values during the week, and then Fridays for whatever reason really drop off. Now let's look at an example of a multivariate time series where let's include something else in the model that might help. So let's look at holidays, right? So just a simple, adding a 1 or a 0 depending on if the data is a holiday or not. We've added that, and you can see it does definitely make a difference. There's fewer purchases on holidays, which might be expected for wholesale purchases. Okay, so again, let's do a little bit more of the seasonality breakdown, and you can see there's a positive trend over time, that sort of standard weekly pattern, and some residuals. Okay, and as I mentioned before, you could also do multiple levels of decomposing by season. So let's do that again here, where we're looking on a yearly basis. I take all this daily data. There's a cleaner trend from a trend perspective, and then you see this seasonal view here. Okay, so this was sort of a first view into how to use BigQuery to run some queries, analyze the data, use AI platform notebooks to understand what you're doing. The next lab here, I'm just going to show how to build a model, right? So that's what we're here for. So I'm going to just skip ahead past a little bit of the setup steps again, but we're loading the data. I have some functions here to scale the data. If you've done this plenty of times before, you might know that sometimes it can help to take data, let's say in millions of dollars, and scale it to say, a hover around a mean of 0. And then when you're finished, scale it back. And that just helps the neural network converge faster. So I'm going to skip it. And then I've got some code to put it into sequences. So then let's actually look at the model itself. So we talked about a LSTM. How would you, looks like I actually might need to run a few of these cells, no problem. Okay, let's just run them. That should be pretty quick. Okay, all right. So here we are, we're going to create a model. So, here's an example of how the model code is actually, there's not a lot of code here. This is very straightforward. A lot more of the work, as many of you may be familiar with, is in the actual data pre-processing. So here, all we're doing is saying we're going to create an LSTM that's got 64 units specifying the shape. And then we have one more layer that is, a dense layer. How many output steps? Like, in other words, how many periods are we forecasting forward? In this case, it's just one, so pretty straightforward. Then we compile the model. We say, are we, what we're optimizing for, what the loss is, we're using something called mean average error because we don't want to square the errors. There's going to be some outliers, especially in that daily data. So we want to smooth that out a little bit. So that's all you do. You know, create the model, compile it, and then you fit on the training data, and you're going to see it run for a while. So I'm going to briefly introduce the next notebook while this is running. So this is an example of running in the notebook, which is perfectly fine. As Yufeng mentioned, you are running inside of one deep learning virtual machine, but you're limited to the size of that VM, you know, the number of CPUs, GPUs, et cetera. Another option you have available to you is to use a service, right? So we have the AI platform training and prediction services. So I'm just going to, I won't actually run that code, but I'm just going to show you another notebook that that shows how you would implement that. So I'm gonna,
Carl, your
yeah,
your previous model, what are you trying to predict?
yeah. Oh, so we're trying to predict sale. Okay, yeah. Sorry, great point. I skipped over that. Let me go to my sort of the inputs here. So I'm taking 30 days of past sales of the liquor sales, and then forecasting 7 days forward. What are the sales we're going to see in the next week? And I've got two features, right? The previous values, like what were the sales in the last 30 days by day, and then whether those dates were holidays, zeros or ones, and then I'm spitting out the next 7 days of sales.
Great, thank you.
Okay, sure. All right. So it might actually be, I think it's wrapped up now. Okay, cool. Okay, so let's now go and evaluate the model. This is a little bit complex, right? Because I'm not just printing out 1 day, I'm actually looking at 7 days. So that's why I kind of have these stats per day. I'm kind of looking at first T+1, like how good was the model at predicting tomorrow's value? Then I have T+2, how good was it 2 days out, so on and so forth, right? So if this was just predicting tomorrow or next month's value, you know, I wouldn't sort of have all these extra graphs here. But let's just kind of look at what this means. That the R-squared value is, you know, 0.739 overall. So across the whole week, what this means is the model explained 74% of the variance. So that's pretty good. And its average error, it was off by 220,000. You know, and the mean is, you know, 1.78 million. So not too bad. And what I'm doing here on each of these different charts is comparing the actual values versus the predicted values. So if you recall, we reserved like 1/4 of the data for testing, right? So from 2018 on, this is the test data. We never trained on it, we never saw the data, and then we're going to, you know, predict on it. And so you can see generally it captured these trends pretty well. This is a tough problem because this is daily data, right? I mean, there's a lot of fluctuations that, you know, any ML model wouldn't be able to capture stuff that's just, we'd have no idea of, you know, some stores closed or whatever that, you know, we have no idea about. But in any case, generally you see things like this where, you know, you start to see, okay, it captured this dip and then tracking pretty well to the overall trends. And so, you know, and we see that forecasting a few days out, the values are, again, hold pretty well the further out you go. So about 7 days out, it's still kind of a similar accuracy level, which is great. So let's also take another quick look here at the CNN. I think we're running a little bit short on time, so actually I'm going to finally show just how you do this in the cloud. So assume that I've already created the model. Basically, I'd create this model code similar to what I just did, right? I have a LSTM, and what I'm doing here is at the very top, I'm writing this to a model py file, and then I'm going to upload it to the Google Cloud servers, and it's going to run this code on the cloud to compile the model. And so I run this command to copy it to a storage bucket. And then here's really where it all happens. I'm running this in the command line. There is a Python SDK, but just so it's clear, I run gcloud AI platform, so on and so forth. I submit a job. I can specify, where the training code is, what version of Python, what version of TensorFlow, and so on and so forth. Then I can check my job status, and then, then I can create the model. All the things that Yufeng showed you in the GUI, you can do here from your notebook. And then finally, I can invoke this command to predict with the model. So again, I think I'm running a little bit short on time, so I'll stop the demo now and see if we have any questions. Yeah. So I'm not exactly sure where the best way to where to start here. Yeah.
Now that we've kind of gotten through all the presentations, I can share since we couldn't get the questions working, I can reshare the questions link that we were using before. From my presentation,
Perfect.
we can just
Let's
use
do
the same one. And so that's on the live stream now. Let me grab, let's see, I'll just type it in here, I guess, into the chat slides, or should I present that window again? That might work. All right, here we are. Oh, that is not the right one. Cool. So hopefully that is working. Are you able to see the questions link? And I'll try to make this a more interesting layout maybe. Great, and that says we can see it. So from there we have some questions that were kind of holdovers, and there's actually a question for Sarah about the what if tool from kind of the tail end of my presentation. Or they still had this open, so that was towards the end of your presentation, actually 1:37 p.m. or Eastern time. But
cool. Yeah, great question. Does the what if tool only work with TensorFlow? The answer is no, it works with any model actually. So if you're not using a TensorFlow model, I think the method is called set custom predict function. You basically just need to call your model and get the format of your data inputs and outputs into the format that the what if tool is expecting. So that is definitely doable. I've used it with XGBoost, scikit-learn models before.
Awesome. Thanks, Sarah. We also have a question here about limitations on libraries we can use, or abilities to install any libraries of our choice. I'm not sure what kind of product they're referring to, but for most things, people can generally use whatever they want, especially if they go into some kind of custom container mode.
Yeah, maybe it was in reference to Cape Notebook. So depending on the instance type you choose, it comes with a lot of libraries pre-installed, but you can obviously easily install any ones that aren't on there.
And then here we have a question about importing and exporting kind of a pipeline for, in a DevOps workflow. Carl, do you have maybe you'll have some thoughts on this one for kind of team structuring?
Yeah, absolutely. So a product you might want to look at, and we had a great blog post recently about it, it's called Cloud AI Platform Pipelines. And there you define a series of steps, and using components. So maybe you have step 1, extract the data from BigQuery, step 2, train a model in the cloud, step 3, version and deploy that model. You define that in Python code, and you can, export that model. Export that pipeline so it can be used by anybody, and it sort of runs in a deterministic way every time. So yeah, absolutely. Check that out, Cape Pipelines.
And then we also have, I think this might be one of our last questions from Stephen Gray about exporting models to the edge to run on things like Coral. Yeah, and I guess generically the answer is sure. You can basically do whatever you want, especially with AI platform training. You can train any model you want, any framework you want, and you have complete control over what that code does, both during execution and what you do with the files afterwards. You can export them to, cloud storage. You can export them as on-device models. There's ways to kind of quantize, and different approaches kind of vary there. And the Coral team has great documentation on kind of that process of using things like TensorFlow Lite and TensorFlow JS to get your models to the edge.
Yeah, there's no lock-in on AI platforms, so you could also do the reverse. If your model trains super fast, you could train it in Colab, you could train it on your laptop, then export it and deploy it to the cloud for serving.
Yeah, and I think the only other question was about time limit of notebooks in Colab. We kind of touched on that there's kind of a not hard, documented time limit, but it does exist. And it's in my anecdotal experience is that it's on the order of 6 hours, give or take. Yeah. Well, with that, let's see if there's any new questions. Feel free to use that link at the top, the slides.app.goo.gl, to post any new questions. But just wanted to, thank everybody for coming today. And I had mentioned that we would have more sessions kind of coming up, one on TensorFlow Enterprise tomorrow. So I wanted to make sure I got that link to folks who are interested. So that's in the chat, as well as a link to, Sarah's and I's conversation about explainability. So if you wanted a kind of more extended conversation about that, you can check that out there. And so I'll drop those into the chat there for folks who might be interested in tuning in.
Thanks for joining, everyone. This is fun.
So it doesn't look like there's any new questions coming in. And I guess, with that, I'll stop presenting. And thanks everyone for coming. People were asking if we'd be doing this again, if there's recordings for this. So yes and yes, I guess. Like there are definitely recorded. This is being streamed to YouTube live, and we're gonna have the same link will live on as a YouTube video. We might trim the beginning or something like that just to make it a little bit easier for folks to get onto. And as Annette adds, if you did not register for this event, go ahead, and if you like to kind of get follow-up and things like that,